Okay.
Yeah.
So let's see. We've got this manuscript. I'm slowly catching up on all sorts of back stuff here.
Yeah.
Okay, so we've got just make sure I've got this here. Google Docs, BCLA, right?
Yeah.
Okay. There it is. Okay. Oh, I see. This is a substantial amount of stuff for me to work on now.
Yeah.
Okay. You've been writing here.
Yeah. Like I
Okay,
said,
good.
the only real stumbling block is the Thomas's data, and I'm not really having a lot of luck getting that analyzed, although I'm still working on it.
Oh, okay. It's not as clean as the stuff from YouTube?
Well, it's just that it takes a bit of time to figure out a strategy for putting a mask on it and then getting them all converted and then getting them analyzed. So.
Oh, okay. Oh, I see. Oh, so it's not the cleanest of the image.
Well, I mean, the image actually, like, you can't just put it into the algorithm and get, like, clean segmentation. You have to play with the image, like the contrast and things like that. That's a lot of the tricks that people use generally. But, I mean, because the background, it's like a grayish background, and then the organism has its boundary, and then it has, like, an interior. Actually, the images that he has captured are a little bit too clean in that sense. Because you can actually, a little hard to see it's easy to see the boundary by eye, but then when you actually try to, like, segment it, it's a little bit difficult.
Oh, okay, interesting. Well, one advantage of working with him is he's also a superb microscopist, so he can change the lighting conditions, the magnifications, he can fragment the colonies so we have smaller colonies. I guess you notice the large colonies tend to form a sort of swirl, like a barber pole swirl.
Yeah.
Okay. Like a band going around, wrapping around a barber pole. So they don't lie flat.
Okay.
So to get flatness, you want smaller colonies, and that's probably quite good enough for us.
Yeah. Yeah.
In fact, I'd like to see them down to. Well, actually, I'd like to see them down to step one. I don't know if he's got a laser to do that. The experiment I did back in the 60s was to zap cell number 2 with a pulse ruby laser and destroy it.
Yeah.
And then we published a small abstract on this. The cell number 1 then went back and forth against the shards of cell number 2.
Oh.
Okay?
Okay.
And it went a certain distance. The frequency varied a bit, and unfortunately, I've lost the data since then. But so the curve was, you know what an FM curve is?
Yeah, I think so. Frequency modulation curve.
Yeah, frequency. So the amplitude is constant, but the frequency shifts a bit.
Yeah.
So it looks like an FM curve.
Yeah.
So what that proved is that the oscillations were intrinsic to the individual cell, and therefore any synchronization is entrainment of those oscillators.
Okay.
Okay.
Yeah.
So it was a simple mind experiment, but it took access to this pulse ruby laser microscope to do it.
Hi, Abraham. How are you? Looks like Abraham's joined us.
Oh, very well. How are you doing?
Okay.
Good morning.
Yeah. The pulse ruby lasers are thought to be uncommon, but you can certainly get a hold of a UV point laser.
But the disadvantage, the UV ones, the advantage of pulse ruby laser is that you can kill one cell on the move. You sort of, because these colonies are continuously moving, so you sort of aiming at a moving target.
Yeah.
I don't know, but if the UV beams can kill a single cell in a very short time, that would work.
Yeah.
And I know that there are UV microbeams also.
Yeah, we have one too.
You have one. Great. Okay, well, maybe Thomas Harpich will send you some bacillariae to look at. Because that experiment,
I'm not sure it's working, but we have one.
well, we should check into it. That would be great. Check into it and see what the question is. What exposure time do you need to kill a cell?
It's going to depend on how much laser power we put out and how sturdy the cell is.
Okay.
And also what magnification we're under. How small is the target?
Well, these are 50 microns by about, I don't know, 5-6 microns, something like that.
Okay.
Typical size. And they're full of chlorophyll, so you could look at anything that would absorb in the spectrum of chlorophyll would probably destroy them.
Well, I will see. Yeah, we have an ILAT system, which is a regenerative destroying laser light system that basically runs using Galvo to put the spot wherever you want it in the field. It's a little vague, and the spot isn't very tight. And right now, I think it's 1 not calibrated and 2 not hooked up correctly.
Well, since we're all going here for killing, the calibration's not important.
Well, calibration is important if you want to be able to, actually put the laser spot into the back focal plane of the lens.
And that's position-wise. Yes, you need to know where.
Yeah.
Okay.
Particularly because the UV laser is invisible.
Right. Okay.
Yeah. And that would require hooking up some of the visible light lasers to it right now, and I think
that's another way to do it. Just get something that fluoresces in UV.
Yeah.
Just add it to the medium.
Usually it fluoresces in UV, yes. Those aren't too terribly hard to get.
Not something that flashes visible with UV light, that's what I'm saying.
Yes,
Yeah.
And fluoresces in a band that I can detect. But that's also not too hard. A highlighter will work.
Highlighter, what's that? Oh, okay.
Yellow highlighter.
Yellow highlighter under a microscope. Don't understand that. What do you mean?
Yeah, so what you do is you take a yellow highlighter and you coat the cover slip with the dye. So it melts that cover slip.
I see. And the UV then heats it.
And then when you fire your laser, you're gonna when you fire the laser, you're going to you'll get spots that come out with basically any laser, any light wavelength that hits a highlighter is going to make the highlighter fluoresce.
Makes the highlighter fluoresce. I see. Oh, okay.
It's daffy, but the highlighter is cheaper, and easier to apply, and you get the image that people bang. Yeah. Some of them even actually have beads, which is even
neat. Okay.
Yeah. That does work. The other thing, there are a lot of worm labs. A lot of the other labs are going to have micropoints that they want to do single cell killing. And for micropoints, the way you check whether or not it's going to work is whether or not focus is whether or not the UV laser can crack cover slip.
Okay. Whether or not what?
The test for a micropoint, which is the one that just has a spot somewhere in the field, is you use it to crack the cover slip.
Oh.
That's the intensity that you use to kill a cell. You crack the cover slip.
Okay, here's, I just put in the chat, this is the reference where we reported the laser microbeam experiment.
Yeah.
Okay, and let's see. Where am I? Okay. Abraham. Let's see if I've got you in my address list here. Oh, yes, I got you. Okay. Yeah, Abraham, can you get specs on that system?
I can do so. I'll also check whether or not it's hooked up and working, and what are the odds that it will function. But I also can pretty easily get you. Yeah, they're not super uncommon, and I'm about 99% sure that ours isn't working right now. So
Well,
in the reason, yeah, we basically had to disassemble and reassemble that microscope, and I haven't spent time trying to recalibrate it, which means that it's not likely to function right now. But we didn't touch that part of the white path, so in principle it shouldn't be a problem, but in practice, yeah. Our institution decided in its infinite wisdom to replace the tubes of the HVAC system in our building, which meant we had shut down our lab for a month.
oh,
Yeah. That meant creating all the microscopes and bagging the room so that we didn't get full of dust.
oh well. Yeah. I once worked at a small computer center where somebody decided to machine polish the false floor with all the, this is back in the with all the cables underneath. And the fine dust that was raised destroyed all of the discs.
Oh.
Discs were not airtight in those days, and they were the size of washing machines.
You have had the students that from the microscope suite as well, but they come in with a little bit of stuff.
Now your voice is breaking up, Abraham.
Just look for that. So please have 1 minute to listen to that.
I can't understand this. Abraham. Okay.
Yeah. Yeah. Okay.
Somebody supposed to talk this morning?
Oh, yeah. Well, I guess Abraham and Dick are the only two, well, along with myself. So I had a presentation to do. I could do it next week. It's if you, unless you want me to give the presentation now. It's a very short one.
Well, maybe find out what's holding the other guys up.
Yeah.
No, next week will be fine.
Yeah.
Then I can have some breakfast.
Yeah.
Yeah, these guys in India wake us up pretty early.
Yeah. So, I guess we could talk about the paper. I guess, I don't know if you had any specific questions about it, or...
No, I haven't read it yet. So
Oh, okay.
I want to have questions before I read it. Okay? Yeah, I'm in catch-up mode right now, and slowly working towards things.
Yeah.
Working through things. So, okay, I'll put that little priority list here, and let me see. Okay. Okay. Good. Okay. We'll work on that. That one's done. Yeah, I also have a history of diatom. I called it the whimsical history of diatom motility.
Oh, yeah. Is that like a book or a paper?
No, this is a chapter for the
Okay.
for the book, same book.
Okay.
Okay.
Yeah.
So, I've got that to work on, so I've got lots to do for this book yet.
Yeah. Yeah, I know. It's like this chapter's like a little bit more challenging, like because they're assembling like this analysis and then trying to.
Yeah, I just reviewed a fun chapter which is about diatoms that get a free ride on bigger diatoms.
Wow.
They seem to specifically attach themselves to large motile diatoms, and then they get all the benefits of motility without having to move.
Yeah.
So, now, I should have asked the guy, do those diatoms have the smaller diatoms that go on them? Next question.
Yeah. So in this book, how many chapters are there? Do you know, or?
Oh, I don't know. Probably around somewhere between 15 and 20. I haven't got the count.
Oh, okay.
Maybe. This chapter will be unique. I can tell you that. The one on Bestlaria.
Oh, okay. But it's just on diatoms and different.
Yeah, the whole book's on diatom motility. Okay. Oh boy, I don't know. That can't be right. Okay. No, I don't have a proper count.
Oh, okay.
Stan Cohn's the lead editor on it, and I'm leaving the paperwork to him.
Okay.
Okay. Okay, so at this point, then I basically have to read the paper.
Yeah.
Okay. Abraham, I guess you. Abraham, you've seen these movies of Bestlaria at this point, right?
I don't know if you've seen the ones from Thomas, because I think he just sent it to us.
Oh, I should send them to Abraham for inspiration.
Yeah, because actually, Abraham Thomas Harbeck, who we're working with, he's maybe that's there's some movies online.
Oh, okay. Abraham's responding in chat. Okay, I see. He's giving up talking.
Yeah.
Okay. Okay.
So, yeah, this we're working with this. He's a microscopist in Germany. He's working out of his house, I think. And he's been collecting diatoms from a local river, and he's been putting them under the microscope. He's actually been culturing them and then putting them under the microscope. And he's gotten some really good video of these colonies. I mean, the stuff that they have on YouTube is, it's adequate, but it's not like, really a really good image. I think so, yeah, yeah. So
Okay,
he's been working on this. He's been actually collecting some pretty good videos. He just shared the videos with myself and Dick, but I'll probably show them to this audience too.
Yeah, let me. Oh, okay, here it is. Okay. Oops. Oh boy. There. Okay. Abraham, if you check that out, you see a lot of beautiful pictures and descriptions of diatom motion.
Oh yeah, his slide. I forgot about that.
Yeah. Okay.
Yeah.
Okay, so I'm gonna have breakfast. We'll call it a day, and hopefully I get to this manuscript in a few days.
Okay. Yeah. Yeah. Let me know if you have any questions.
Okay, and maybe pick Abraham's brain in terms of trying to get these pictures analyzed.
Yeah. Yeah. It'd be good.
Okay.
Okay.
Okay. Have a good day, you guys. Bye.
All right. Bye. Oh, bye. Okay. Oh, here we go. Hi, Jesse. Hi. Yeah, glad you could make it. We've been talking about some paper that you're not involved in, and we've been talking about some other things. So, glad you could make it. Okay. What's new? And this goes for Abraham as well. You have anything to report or? All right. Well, actually, I wanted to talk about. Oh, okay. Not from the ML side. Do you have anything else? Like, do you have anything in terms of like some of your other work that you wanted to talk about? Okay. Abraham still has an unstable connection. Okay, that's good. Okay. Not for you. Okay. Well, I wanted to talk about a couple of things, I guess. We'll probably talk more. I had a presentation, but I'll give that next week. And then we also have the pre-trained model blog post that I had mentioned in the email. I haven't really worked on it very much. So let me share my. I don't know if Jesse was here for what we kind of mentioned it at the end of last week's session, but let me share my screen, and I'll show you what we're thinking here for this. So this is building on the conversation we had about pre-trained models 2 weeks ago, and so I had the idea that we should create a blog post for this topic, and we could publish it on the Node, which is the developmental biology blog, and maybe get some feedback on it. So it's like I've said, I think last week, and thinking about shooting for about 1,500 words. So it would be broken up into a couple parts. The first would be, what is a pre-trained model? So we kind of go through this short description of what a pre-trained model is, and it should be at a very general descriptive level. So it shouldn't be too technical. But what's important here is that we kind of mention what's of specific interest to biologists. So this would be pitched at biologists, but also, give them enough information to make them think about maybe using one. Then the problems for application of biology. So, there are some issues with applying it to biological questions. And again, we want to make it attractive to biologists so that they can think through the implications of this. Because I think a lot of biologists probably don't know about this specific tool. Maybe they know about machine learning a bit, but maybe not this specific type of model. And then, that involves talking a little bit of input and training data, the concept of a feature space, and then talking about models and biological problems. So this is more sort of philosophical, but that's probably important as well. And then the third part would be modeling a biological image. So the idea would be you'd model an image or a set of images in this kind of model, and there are a number of things to consider. So I think one thing we pointed to was that we want to model a bunch of different tasks, like a very general pre-trained model, or do we want to focus on a single set of attributes? If we were to create some sort of biologically specific pre-trained model, does this allow us to have context that cuts down on the amount of training data that we would use? That's another point that we had. And then this issue of blobs versus symbols, which are rival strategies for processing data. And on that last image, I've actually got some resources, and I've put them on the resource page. It's not this one. There's this debate in the machine learning community. I think these these 5 references that kind of talk about them. It's the idea that you can have either, throw data at a problem and extract features and solve a problem that way, or you can use a system of symbols or a representation to model a phenomenon. So, this has been a long-standing debate in the history of AI, where we've had, people like Gary Marcus, who's a cognitive scientist, who's argued that we can use symbolic systems to achieve this sort of artificial intelligence. And then there's another group of people who say, well, if you throw a lot of data at a machine, if you throw just enough data at a machine, and it could be like, terabytes and terabytes of data, but that's actually better than a symbol manipulation system. So there are these 5 references on this page here that kind of go into this debate, and it's a little tedious at times, but it's basically the idea of if you know anything about nature nurture in biology, where you have, on the one hand, you have machines that have no prior knowledge of something, and then they're learning from data that's presented to them. On the other hand, you have maybe like a machine with a representation, which would be like some sort of inherent knowledge about something, but not specific knowledge, and then the data would fill the gaps. So, it's like the difference between innateness and the blank slate. And so this paper actually in particular is really interesting. This is a new one by Anthony Zador, and he's been involved in this debate. He's basically saying that we need representations that have like a genetic basis. So they're using like a innate encoding to aid their models of intelligence. So, I mean, I don't want to get too far down that rabbit hole, but I was thinking that would be a good way to summarize this last part of the blog post. So, like I said, I haven't really had a chance to work on it since last time, but so let's see. Jesse has a question. Because I want to go more into that symbolism versus data debate myself. There's a list on Slack. Oh, I can put that stuff on Slack. No problem. I'll put it up on the OpenWorm Slack and then maybe on the orthogonal Slack, and I can send Abraham an email or, something like that. That's just a copy paste thing for me. So I can just, but yeah, I mean, I just wanted to give you an idea of what I was thinking for this post. Maybe this week I can get a chance to flesh it out a bit more, and I can send you guys some of these references for the final part. I can come up with some basic sort of, I have an outline now, but like some basic text that we can play around with more. And then if you have any ideas, you can add in. Well, we're kind of aiming towards 1,500 words, so we're going to try to get it. We can make it bigger, but then we're going to have to cut it. That's always the challenge with blog posts. That getting it brief enough so that people can read it in a short burst and then get something out of it. I found that if you try to do these really long blog posts of several thousand words, that people tune out. I don't know if it's because you're on a blog or because that's just what people tend to do for long papers, that they just read the first part, and there's a limit to what they want to read on a topic unless you make it super compelling. But and then, like I said, we can post it at the Node. I don't know if Jesse's familiar with the Node. It's a developmental biology blog that people can submit content to. So you just submit a post and it's posted. You have all sorts of people posting different things there, but it'll give some exposure to that community. And that's kind of what we want. It's I don't know. We'll see what happens if we can get this finished and published there. I mean, the advantage of that is it has a big audience. So what do you guys think about that? Do you think maybe over the next few weeks we'll kind of work on it some more and get it fleshed out in terms of complete sentences? I mean, I'm just taking this outline from the conversation we had, so it's we're all kind of contribute. I think Abraham and myself, we were in this conversation, and then a little bit with Vinay, and then Jesse's perfectly welcome to add things in. Yeah, that's fine. I mean, especially if there's I think in your case it's there's a way to do this to gain some expertise in the area by reading some things. So, okay, I don't know what happened to Abraham. He dropped out of the meeting, but his connection wasn't very good. But and then I guess for Jesse, let's see, the other thing I had, and I don't know. Well, I'll mention it now. I've been talking with someone who had another collaborator. He was here before, Aiden Rock, and we were talking about doing sort of a distill for developmental biology. So let me show you what distill is. I'll probably talk about this next week. Seems like this week wasn't working out very well. So this is distill. It's a machine learning blog. It's actually a journal that they have. So people publish articles on here. and it's different topics in machine learning. And hi Abraham, welcome back. I was just showing Jesse about this journal that they have in machine learning called the Still. And okay, good. And it's unique because these are like journal articles that people publish and submit to the journal. Well, what's unique about this type of journal is that you can publish articles with interactive features in it. So here's one where you have like this animation in the paper. And then the paper is, it's like a regular academic paper, but you can embed demos in the middle or animations. You can obviously put in your equations and all that. But the advantage of this is that it's not sort of cast in PDF. So people can interact with the article, and it's a lot less static than a PDF. And so I was actually talking to Aiden about this, and he wants to start one for developmental biology or computational developmental biology or whatever it is. So we're going to sort of work on that as well. So that means that of course, we're going to be recruiting content for it. But it may be just, a couple people too, depending on who wants to be involved. I think his idea, though, is to create this infrastructure. He already has like an infrastructure. Yeah, we'll talk about it more in coming weeks. He already has the infrastructure. He has a blog, for example, where he's kind of done this sort of thing before. So, the idea is to have a venue where, it can showcase ideas, and it's kind of a niche because that sort of niche isn't really filled right now with a journal. We have, some journals in developmental biology, some journals in, computational biology and machine learning, but nothing in that specific area. So that's another thing I wanted to point people to. I think that's all I wanted to talk about. So, Abraham, now that you have your audio back, did you have any thoughts about the blog post or? Oh, well, I was just going over the blog post. Why don't I do it again? Oh, okay. Why don't I go over it again? Because let's see. Okay, here's the blog post. So this is getting it down to about 1,500 words, and we would have like 3 sections to it. So the first one is what is a pre-trained model, which is defining what this is for a biological audience. So we'd have a short description of what it is. Kind of like a very brief survey of the current models that exist. So, you have specialized models for language, you have general models for just like, objects, but nothing for biology specifically. And then, what is of specific interest to biologists about pre-trained models? I like to think about it as like maybe it's a part of deep learning, but it's also maybe, a method like any other type of machine learning that might help people analyze data and create a model for understanding their, generalizing to different types of similar data and things like that. Then like a section that would be a problems for application of biology. So, we talked about in our discussion the amount of input and training data. So would a pre-trained model reduce the amount of data you would need to train a model? Then we can talk about like a feature space in terms of biology. So, is the feature space, what does it look like? Are we talking about like, genes? Are we talking about phenotypes? And then a discussion about models, and that's more philosophical, as I was telling Jesse. So there's this idea of models being useful, but not, but not like the actual phenomenon. And then like this idea of that maybe you have to customize a model to biological problems in order to make them more useful. But that, I know it's philosophical, but we want to make that very brief. And then the final section is modeling a biological image. So this is like, the idea that you have, we're taking a biological image and we're doing things to it. And then we had, and part of our discussion was, do we have to model a bunch of different things, or can we model a single set of attributes? We also have the idea of adding context to the image, and then this thing about blobs versus symbols. And for that, I pointed to these references here in our tutorial resources. So there's this debate about innateness versus like a blank slate, where you either can just throw data at a problem, and if you throw enough data at it, you can solve it, or just having like a general representation, which is the way to like make it solvable. So not to get too deep into that again, but to like just kind of point to that area and see if it's like relevant to biology. So like I said before, this is something I'm going to try to flesh it out a bit more in terms of complete sentences, but hopefully, we can work out over the next few weeks. Maybe we can work out it in the meeting, or, whenever we have time, and then we can get it fleshed out. If you have any ideas for like additions, or, please let me know. But I wanted to try to keep it brief, just as a single post. We might build onto it later in subsequent posts.
Yeah, I think that all looks pretty good.
Okay.
I mean, is my audio working now? Yeah.
Yes, you're coming.
Oh, good. Okay, cool.
Yeah.
Yeah. I think that all looks pretty good. I think the only additional thing that may be valuable is if we have some exemplars. So examples of models that exist for specific biological tasks. Having concrete examples will certainly help convince people that this works, if nothing else.
Yeah.
Yeah.
Like, can you think of things that are at the top of your head that we could like turn to as examples, or?
I mean, in the image segmentation space, there are a bunch of implementations of UNet that have been trained to do specific sorts of things, and have done pretty well at segmenting biological data in a binary fashion. Although a lot of that's been done with like MRI images.
Yeah.
There's a number of neuroscience that exist that are modeling neural networks and neuron behavior. I don't work on that anymore, so it's very rusty in my head. I know that they exist, though. I don't have any other good examples offhand, unfortunately, other than the ones that I'm using and I have used in the past. But I know that they exist. I think that there's a whole project out of the Allen Institute to try to basically guess where different subcellular components are within cells based on phase contrast images.
Okay.
and there's some, should we say, controversy about whether or not the method is legitimate, but the model exists and give you a reasonable model of, sort of what the bleeding edge looks like in terms of what you can get from a machine learning model, of biology at least. It's just unclear whether or not the underlying stuff corresponds with physical reality or if it's just arising from the network.
Oh, yeah. Well, that's actually a good point.
Yeah.
That, you have this issue of like things that arise. Well, actually, that was kind of what the talk I was going to give was on Pareidolia. Like, you can generate things that look like they're real, but yeah.
There's also a really nice thing, I think it was from Google Maps team, where they were trying to train a network to identify structures and buildings, and it just figured out a way to stenographically encode the information in the output images so that it could carry information forward and cheat.
Yeah.
So there's some little interesting things that can happen, where they tried to build a neural network to segment satellite data, and instead they got a neural network that could do really good sonography. Yeah.
Yeah, it's it doesn't really model the thing that they wanted to model, but they got something. Fortunately, they got something out of it, but yeah. I mean, that's probably good. I mean, there are probably not going to be a lot of examples that exist. That's why we're want to do the blog post, but just give, I guess, give some sort of, maybe, this is basically what we're trying to get at here. These are the challenges.
Yeah. Concrete stuff's going to help.
Yeah.
With the audience in particular. Yeah.
Jesse, did you have anything to add to that?
No. I think the distill thing you mentioned at the end was for another project.
Oh yeah, this is for something else. It's actually just something I wanted to point people to as something that's sort of starting up. I don't really know the details too much, but that's something we're working out. So, the distill thing, distill is this interactive journal that they started about 2 years ago, and then the idea would be to create articles that are dynamic, where you can have animations and things like that, where it's not constricted to the PDF. I mean, other people have done versions of this, but and I think Aiden's figured out a lot of the technical aspects to it. So I'll report more on it when maybe there's something, when we can see the sort of the outcomes of it. When we have something published on it. Just keep you updated.
Okay.
Yeah.
But yeah, both of the items sound interesting, and I'll definitely be interested in. Again, I don't know very much, but maybe that would be a way for me to kind of use my beginners learning stuff to contribute to the blog post, because I'll probably be a sort of target audience at best for that. But yeah, no, I'm definitely interested in that, and I'll just, if you could, I don't know where to look at the blog post that the notes that you have about it. So that's going to be.
Let me see if I can give you a link here. I can put it in the window.
Okay.
So this is the document, and I have it shared.
Okay. I'm going to have to go back off of this again, but I will. Okay. Yeah, I know the meeting's almost over too, but
yeah.
I'll be around.
Okay. Yeah. Thanks. So yeah, I can send that information out again in an email, and then like I said, with the blog post, I can work out some of the complete sentences and add in what we just talked about with examples, and then we can just keep working on it over the next couple weeks. So, and then next week I was going to present this talk on computational pareidolia this week, and I kind of previewed it a couple minutes ago, where I said, there are machine learning techniques that people have found that they can create, sometimes their outputs are, they output things that look like patterns, but they're not. And so that resembles something in human perception called pareidolia, which is where you see things like faces and objects where there's no face, but it looks like a face. And so, I have some interesting things to talk about there, but I'll keep that for next week. And then, if anyone has any other questions,